Well, class, I hope you're enjoying the rain. And chapter 6. So, chapter 6 was all about the electron. That has brought us up to this point of being able to write electron configurations. And when an electron configuration is describing, describing where the electrons are around the atom. And that behavior, where those electrons are, ultimately explains the behavior of different atoms, why they react with certain things, why they bond with certain things, why they have 4 bonds or 2 bonds or 1 bond. All that's related to where the electrons are around the nucleus, especially those outer electrons. So let's get at electron configurations. So each part of the electron configuration communicates a certain thing. So the first part, the first number, tells us the energy level that we're talking about. So in this example, we've got the 4th energy level. Then the next part, the letter denotes the type of orbital it's in. So the P, so it could be the S, the P, the D, or the F orbital. And then the last one is the subscript indicating the number of electrons in that particular orbital. When we write, so another way that we might write electron configurations would be using orbital diagrams, using boxes to indicate individual orbitals with numbers or headings underneath. So each box in the diagram represents one orbital. So if you're talking about an S orbital, you're going to have 1 box. If you're talking about a P, you're going to have 3 boxes. If you're talking about a D orbital, you'll have 5. And then if you're talking about an F, you'll have 7. Half arrows represent the electrons that are filling those orbitals, and you notice one's pointing up, the other one's pointing down for a filled one, and that goes to the idea of the Hund's rule that you can only have one electron in the exact same, in one location of the atom. So the direction of the arrow represents the relative spin of the electron, so that ms value that we were looking at earlier. So in Hund's rule is the idea that for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. So Hund's rule is the idea that we fill them first pointing up, and then we go back and point them down in the same orbital. So S orbitals, you don't really need to worry about it because you only have one orbital. But when we're talking about the P, the F, or the D, then you would fill all in the same direction, and then you would go and backfill going the opposite direction when filling. Okay, so how does this apply to the periodic table? Ultimately, the periodic table is broken down into the different orbital shells, and the periods are associated with the energy levels of an electron configuration. So we fill in order. We go from the 1s, 1s2, and then 2s2, 2p6, 3s2, 3p6, 4s2, and then we go into the 3d section because 3d, rather than being up in the higher level, like after the 3p, it's actually, the 3d is higher energy to fill than the 4s, so we fill the 4s first, and we kind of move through. So each section of the periodic table represents a different orbital shell. The D's, so when defining what number should be in front of the D's, we always subtract 1 from the period that it's in. So if it's in the 5th period, then you're going to subtract 1 from the 5th period, and then you would be filling in the 4D section. And then for where the F's come into play, they follow the 6s and the 7s, but for the F's, they are -2 from the orbital shell, or from the period number. So if you're in the 6th period, you're going to be in the 4F. Now, we'll go over this in class as well, but there are some irregularities when we are filling electron configurations. Some actually break the rules when you get to half-filled orbitals. So when there aren't enough electrons to half-fill s and d orbitals on a given row, things get kind of pulled around so that you can kind of fake fill them. So one example here is copper. So copper has 29 electrons. So what you would think, if you were to write the electron configuration, just following the rules, you would think it would end with 4s2 3d4, or sorry, excuse me, 4s2 3d. Wow, that is total typo. It should say 4s. Man. Okay, so copper, if you look at it on the periodic table on this diagram, not the written stuff on the right, you notice that copper is 3d10 4s1. Okay, so you would think that you would fill the 4s2 completely and then just have 3d9. But what turns out, as far as stability and what the actual electron configuration is that one of the electrons from the 4s is pulled out and drops into the 3d, so that you have the 3d block completely filled to 10, and then the 4s is just missing 1. So it's slightly different modification there. And this occurs because the 4s and 3d orbitals are very close in energy, and so moving that electron gets things more stable. These anomalies occur in the F block atoms as well, so you can kind of look at where they split. So if you look at atomic number, you can see like atomic number, I don't know. Anyway, we'll look at it in class. All right, that's it, and I will see you in class tomorrow.